In this video, we will learn how to multiply two polynomials. Let us start with basics of multiplication of polynomials. We already know how to multiply two binomials. For example, if you have been given two binomials of the form ax plus b into cx plus d, then you know how to multiply these two binomials. That is, we will use the FOIL method. However, in this context, we want to generalize the settings for multiplication of polynomials of arbitrary degree. So let us start with some simple monomials through examples. So here is a polynomial given to you. Px is x square plus x plus 1 and qx is 2x cube. The question is, do I know how to multiply these two polynomials? Remember, this one is called monomial. It has only one term. So a standard rule of multiplication will mean, we have seen this in our quadratic functions, that I will consider the product in this manner. Once I consider the product in this manner, what we will do is, we will try to multiply each term of this 2x cube with each term of this polynomial. So there are three terms, and for each term this 2x cube will be multiplied. So if I do that, the law of exponents will apply. For example, x raised to 2 plus into x raised to 3 will mean x raised to 2 plus 3. So once we apply the law of exponents and add the exponents. Obviously 2 was a constant coefficient of x cube which will be multiplied throughout the expression, and therefore the resultant is this, which we can simplify as 2x raised to 5 plus 2x raised to 4 plus 2x cube. This is how we will multiply a monomial. Now, as you can see, this polynomial has three terms, 1, 2 and 3. So it's not a binomial, it's a trinomial. So my FOIL method will not work here. So FOIL method will work only for these kind of expressions which are binomials. So let us go ahead and try to consider a similar expression, that is a quadratic expression, and another binomial, and try to see how can I extend the basis of binomial FOIL method. Right? So here is a binomial 2x plus 1, and here is a general polynomial, quadratic polynomial, which is x square plus x plus 1, same. Now what will you do? So naturally you will consider px into qx, which will be written in this form. Now if I want to extend the basis, whatever I did for monomial, that means I need to convert this into two monomials. So what are those two monomials? One monomial is 2x, another monomial is 1. So if I treat them separately, that is, if I write them in this manner, let me erase this. That is, I have written them in this manner. Then what can I do about it? That means now this turned out to be a same expression. Instead of x cube, here it is x. That's all is the difference, right? So whatever I did here, I can do it here, and the last term is actually multiplied with 1, which is suppressed, because multiplication with 1 will not change anything. So I don't have to worry about the last term. Now I will multiply this 2x with all the terms of px, x square plus x plus 1, which is similar to this particular thing. So I will get 2x raised to 1 plus 2, x raised to 1 plus 1, 2x, x square plus x plus 1. Now the job is very simple. You can treat this as one polynomial and this one as a second polynomial. And then we have to add. How we add polynomials? We will add polynomials by matching the exponents of x. So if I want to add these two polynomials, what will I do? I will simply match the exponents and I will add them, which is given here. So in this case, 2x raised to 3, there is no competing term for x raised to 3. so it remains 2. X square comes here and here, therefore I added the 2, which gives me 2 plus 1. In a similar manner, the terms containing x are these two, so I have added these two, so 2 plus 1x plus 1, which is similar to what we have seen in the last video of addition of polynomials, and therefore we get the answer to be equal to 2x cube plus 3x square plus 3x plus 1. So effectively what we have done is we know how to multiply the terms term by term, and finally if at all I want to seek an extension of a FOIL method, it will be a term by term multiplication of polynomials. That means you take the polynomial of least degree and multiply it with the polynomial of highest degree term by term, add those terms, match the powers, and then write your answer. So this is one prototype that we can follow for finding multiplication of polynomials or result of the multiplication of polynomials. Now the next question is, can I generalize this method or can I answer it programmatically? That means, can I give a simple formula for what the coefficient of one part x raised to m will be? For example, in this case, can I give a general formula what will be the coefficient of 3x square provided I know polynomials px and qx. So to answer that, let us go ahead and try to find a general formulation of this formula. Let's go ahead, and if you are asked, given one quadratic polynomial and one linear polynomial, you are asked to compute px into qx. How will you go about this? This is what our task is now. So naturally I will write px into qx, and then I will convert each of them into monomials. That is, one monomial will be b1x and the second monomial will be b0. In this case, what will happen is we will simply multiply them as a separate term by term multiplication. So in earlier case our b0 was 1 when we studied one example, but here we are considering a general expression and none of the expressions are 0. That's what we are assuming. None of the coefficients at a2, a1, a0, b1 and b0, none of them are 0. For example, if you consider b0 to be equal to 0, then this term itself will vanish. The second term itself will vanish. You will not have the second term. So we are assuming that all terms remain in the loop. Okay. So now it's simple. The job is multiplying these two polynomials and you will get some answers. It's okay. But now our main worry is to find a pattern in these answers. Okay. So now when I multiplied this, if you look at this particular expression, that is a2b1 x raised to 2 plus 1, a1b1 x raised to 1 plus 1, a0b1 x, a2b0 x square, a1b0 x, a0b0. Here you take a pause and examine the terms. For example, this term contains the coefficient of x raised to 3. This is 2 plus 1, so x raised to 3. So in that case, what is happening here is, if you look at the suffixes of the coefficients, this is a2, this is b1. So together they will sum to 3. In a similar manner, you look at this term which contains x square and you look at the suffixes of the coefficients, that is a1, b1. Together they will sum to the exponent, that is a1 plus 1 is 2. So this should be a coefficient of x square. Then if this logic is correct, what should be the coefficient of a constant? The coefficient of the constant, that is x raised to 0. So the coefficient of the constant must be a0 b0. In a similar manner, you can ask the question, what is the coefficient of x? If you ask that question, you will naturally get the answer. You collect all the coefficients such that their suffixes will sum to 1. That is a1 b0 plus b0 b1 a0. So is there anything called b1 a0? Yes, it is here. So this, what we have actually done is we have figured out a pattern. That means if I want to find the coefficient of x raised to k, then better the sum should be some aj and b k minus j, so that they both will sum to, it's not equal to this is I am saying x raised to, coefficient of x raised to k will be equal to of the form aj plus bk minus j. So with this understanding, let us go further and try to rewrite this sum. So once I have rewritten this sum, my analogy is further amplified. For example, if you look at the coefficient of x square, yes, it is a1 b1 and a2 b0, which is the coefficient of x square. So that also means, this means if I can sum over this j from 0 to what point? To a point where I want the exponent is raised to k, then I will get all possible combinations where sum is actually k. In a similar manner, you can pause this video and verify whether you are getting the same expression for x raised to 1 and all others, right? So with this understanding, I am ready to generalize this demonstration or this theory for a polynomial of an arbitrary order. Let us consider polynomials of degree n and m and try to find the general answer for them, and that answer will be in this form. So if you are given a polynomial of degree n px, and if you are given another polynomial of degree m qx, let us say m not equal to n. Even if m is equal to n, it doesn't matter, but for our purposes, let us take m not equal to n. Then what will be the coefficient of each of the x raised to k's? The coefficient is actually given here. Summation over j is equal to 0 to k, aj bk minus j. This is what we have figured out in this expression, is the coefficient of x raised to k. Then the question is how far the degree will go. The degree will go till m plus n. When m is not equal to n, if m is equal to n, then the degree will go to 2n. That's okay. So k is equal to 0 to m plus n, and each of the coefficient of x raised to k will be j is equal to 0 to k aj bk minus j. Now let us demonstrate this idea with one example. Let us go ahead and see one example of this idea. So now you have been given two polynomials, two quadratic polynomials, and you are asked to compute the multiplication of these two polynomials. One way is very simple. You will go with term by term multiplication, and it simply means you have to multiply the terms of second polynomial with the first polynomial in a term by term fashion. Or you can actually use the formula that I have given you in the previous slide. So you can pause this video and try to compute by yourself, or you can go along with me. So let us recall that formula again. That is px is equal to summation. So my polynomial is a polynomial of degree n and qx is a polynomial of degree m. In this case, in this particular example, the first polynomial is of degree 2 as well as the second polynomial is of degree 2. So in order to find the product of these two polynomials, what we need to find is, we simply need to find the coefficients of x raised to k. So let us first identify what are ak's and what are bk's. J is a dummy index, so it doesn't matter. So let us first identify what are ak's and bk's. So a naught, as you can see, is 1, b naught is 1, a1 is 1 again, B1 is 2, correct, this is correct, and then A2 and B2 both are 1. Yeah. So I have enlisted all the coefficients of this particular expression, Px and expressions Px and Qx. Now we need to use this formula, this formula which gives me the sum. So let us use this formula and figure out. Remember, all the coefficients that are not listed here. For example, what will be A4? If at all I will write A4, what will be A4 in this expression? It will be 0. What will be A3 in this expression? It will be 0. So all the coefficients that are not listed here are zeros. Keep this in mind and try to answer the question. So now computation of coefficient. It's very easy. So let us start with 0th degree term, that is constant term. So here k will be equal to 0. So the summation will actually go from j is equal to 0 to 0. That means it will have only one term, which is a naught b naught. What is a naught b naught? Look here, 1 into 1, so it will give you 1. Okay. Let us go for a degree 1 term. So j is equal to 0 to 1. J is equal to 0 to 1. So it will have a naught b1, a naught b1 plus a1 b naught, a naught b1 plus a1 b naught. These two terms are there. So let us compute them through this table. A1 is 1, b naught is 1, so this will retain 1, a naught is 1, b1 is 2, so it will give you 2, so together it is 1 plus 2, which is equal to 3. Let us go for a second order term, that is the polynomial, a monomial with degree 2. So in this case, j will run from 0 to 2. So I will have a naught b2, a1 b1, a2 b naught, a naught b2, a1 b1, a2 b naught. This is correct. Just go ahead and compute these terms. A naught is 1, b2 is 1, so you will get 1, a1 is 1, b1 is 2, so you will get 2, and a2 b naught, that is a2 is 1, b naught is 1, so you will get another 1, so you will get the sum to be 4. Let us go for a third term, the x cube term, and just simply substitute this. So we need to find all possible combinations. So if it is a degree 3 term and we start with a naught, it will be a naught b3, a1 b2, a2 b1, a3 b naught. These are the terms. Okay. And then you simply compute them. Remember here, now we came up with b3. What is b3? b3 is not listed here. That means b3 must be 0. In a similar manner, here a3 must be 0. Correct? So these two terms are chopped off right away. They are 0. So let us focus on the other two terms. The first term you can easily verify because b2 is 1 and a1 is 1 and a2 b1 is 2, a2 is 1, so it will be 2. So 1 plus 2, 3. This is correct. Now the final term is a degree 4 term. Correct. If you do a term wise multiplication, what you will come up with is, because the degree 4 will be contributed by the highest order terms, so you will simply multiply x square into x square and you will get only one term. But in this formulation, what we are doing here is we are taking all possible terms of degree 4. So even though they are 0, we will first list them and we will put them as zeros. So now when we consider degree 4 term, I will get a naught b4, a1 b3, a2 b2, a3 b1 and a4 b naught. So all these terms are here. And most of the terms will obviously be 0. Only one term is a contributor. For example, a naught b4 is 0, a4 b4 will be 0, a1 b3 is 0, a3 b1 is 0. Because why? Because b4, b3, a3, a4 all are 0. Only term that will contribute is A2 B2, which will be 1 into 1, so 1. So this gives us a clear cut answer, and this is a systematic way to multiply two polynomials. Therefore, the resultant polynomial px into qx, simply write the terms from this table. So this is the coefficient of x raised to 0 is 1, so the constant term 1 is here. Coefficient of x raised to 1 is 3, so 3x is here. In a similar manner, x square, coefficient of x square is 4, so you will get 4x square here. X cube is 3, so 3x cube, correct. So this is also done, and then x raised to 4 has only one term, is 1, so x raised to 4. Therefore, you got the resultant polynomial to be equal to this. Now remember, one side note, the multiplication of two polynomials will always fetch you a polynomial again. Next operation is division, which we will see in the next video, but the division of two polynomials will not always lead to a polynomial. We will see that in the next video. Bye for now. Thank you.